Hello, and thank you for joining us. Today we'll be discussing how to get maximum value from your oil analysis program. This presentation provides an example of the type of material covered in Noria's machinery lubrication and oil analysis training courses, which are offered publicly, privately, and online. At any time during the presentation, you may submit questions in the Q&A window. If you don't receive an immediate answer, a Noria consultant will respond via email after the webcast. As part of our mission to make the world better through lubrication-enabled reliability, we have included a list of resources you may find helpful. Now I'll turn things over to our speaker, Noria's Bennett Fitch.
Thank you, Jason, and thank you all for joining us today. My name is Bennett Fitch, and I will be your presenter for today. This webinar, which is the most recent in a series of webinars Noria has offered over the years, is intended to extend our mission at Noria, which is to help companies enable reliability through better lubrication processes. For nearly 20 years, Noria has focused on the advantages of lubrication excellence to transform organizations for optimized reliability. A successful lubrication program is designed to leverage numerous technologies to maximize the potential return on investment. Oil analysis is one of these most powerful tools in the arsenal of a lubrication program. The objective of this webinar is to provide you with a better understanding of the complexities of an oil analysis program and provide some of the key data points to look for on your reports. I encourage you to ask questions you may have throughout this webinar. There is a Q&A box in this webinar's interface which will allow you to direct your questions to our team of Noria consultants we have here today, ready to respond to your questions as I continue along with this webinar. And at the end, if there's still questions unanswered or we have ran out of time, I'll personally ensure that all these questions are answered. Before we get started, I'd like to tell you briefly about myself and some of the resources available to you. I know many of you might be quite familiar with Noria, but I would like to remind all of you about our publications, such as Machinery Lubrication Magazine and other various newsletters that we have. This content, along with our Machinery Lubrication website, is all made available for free and is dense with information on oil analysis and machinery lubrication. Particularly our website, which makes searchable tens of thousands of articles, white papers, and other various content. Noria has a wide variety of education and consulting services. For example, our training programs include machinery lubrications levels 1 and 2 and oil analysis courses up to level 3. As one of Noria's senior technical consultants, I am the instructor for many of these oil analysis courses. I also oversee our lubrication program development services, which maximizes oil analysis along with other machinery lubrication principles to integrate and optimize the opportunities for lubrication programs all around the world. But of course, oil analysis has always been one of my preferred subjects to talk about, so that is why I'm excited to be here today to talk about that with you. To get started, let's consider what oil analysis is and what are we trying to accomplish. A few years ago, I surveyed a few people to ask them this question. I wanted to get a better idea on what people understood as the end goal of oil analysis. Most responses were pretty good and valid to a point what value can come from oil analysis. They may have included knowing if or when my machines are going to fail. That's pretty important. Detecting and anticipate machine failure early. Yeah, the sooner the better, right? Knowing when to perform an oil change on time. I think that's a good thing to be able to figure out. Better understanding contamination levels. And optimizing machine reliability at the lowest possible cost. There's a lot more to this tool, though, than knowing when to just change an oil. As I wrote in an article published back in 2016, a unified answer to this question can be surmised. The end goal of oil analysis for end users is to aid in the optimization of plant-wide reliability by proactively monitoring various indicators within the oil of individual machines. Pretty simple, right? This should be what motivates us to design our oil analysis program efficiently. And this same motivation will also be the deciding factor when evaluating each aspect towards selecting and working with a laboratory and how to develop your oil analysis program. While working through these decisions of an oil analysis program, make sure you ask yourself, is this aspect critical in helping me reach my end goal of oil analysis? Oil analysis is all about knowing how to ask the right questions and then knowing how to find those answers. You must interrogate your machines. Just like when you go in for a blood test, when you go to the doctor, you're not simply just curious about the constituents of your blood, such as the red and white blood counts, or your platelet levels, or hemoglobin levels, and what those are. All that kind of information alone doesn't really tell you much of anything at all. Although if you were a medical doctor, if you are a medical doctor and trained to be able to convert that seemingly trivial detail about your blood and then turn it into very useful facts about the state of your body, it can become very important. In fact, there are hundreds of details that can be answered by taking a blood sample and sending it through the right types of analytical instruments. But when a blood sample is taken, it's not typically sent through every single type of machine out there to analyze your blood. There's typically a specific question the doctor is trying to answer. There will be different blood tests performed depending on the routine precautionary checks, or if there are specific types of symptoms your body is already experiencing, or maybe the tests are simply trying to confirm a diagnosis. You have to interrogate the oil in your machine. So a doctor may first, once you go in for a checkup, ask you, are you hurting? Where does it hurt? Do you have a sour stomach? These kind of questions. Are there scrapes and bruises? Whatever it may be, these kind of questions may be very similar to how you look at your own oil when you're doing oil analysis. Are there things your machine is experiencing right now that you see through oil level inspection, sight glass inspection, bottom sediment water bowls? Maybe the temperatures are different. Maybe you're hearing things differently. Maybe the vibrations are differently. What's going on in your machine that can give you clues to figure out whether or not you need to adjust your oil analysis differently? Or if it's simply just a routine oil analysis being performed, there will be standard tests that you may want to run so that you can trend data over time to give you the quality results. So in order to help you figure out what questions you want answered, you need to know what oil analysis could potentially tell you. Now, there's different stages in which you may want to perform oil analysis, and some are going to be more cost-effective, more potential savings in return, such as testing new oil or testing a machine before it's failing. So when something is occurring that could potentially lead to failure, you're going to be looking for some sort of root cause in oil analysis. That could be such things like particles or moisture, viscosity changes. All these things that which, if they are abnormal, it doesn't mean your machine is failing. It just means that it could potentially lead to a failure. And if you're catching those root causes before that failure and doing something about it, then you're being proactive maintenance. The savings at this point are going to be the highest. Now, of course, you could be having some wear debris being present in your oil analysis, in which state the failure has already began and now you're in a predictive zone, predictive maintenance. So if it's an incipient early fault detection stage, then you may be seeing abnormal wear in your oil analysis, but really you're not seeing much else happening on the machine. Maybe the viscosity hasn't changed, or maybe the vibrations haven't changed, and everything else seems to be normal, but there's wear debris showing up. If you can figure out where it's coming from and figure out what the failure mode is, or even see what the root cause might be, then you're able to develop a problem diagnosis, and you're going to be going a little more detail with your oil analysis. And if it's a little bit too late, maybe things have got a little bit too extreme with the wear, and there's more wear debris than you'd want to see. You want to know how severe is it, or how threatening is it to threatening of the condition. How much time left do you have before the machine may start to catastrophically fail and come to a stop? Are these corrective actions potentially possible to be done before it fails, or do you simply need to act quickly to get all the right labor, all the right spare parts, and everything planned properly so that when it potentially does fail, or before that point, you can get things prepared and not waste time when it's shut down? Or potentially, let's say a machine fails, unfortunately, catastrophically, you can still do something with oil analysis through a post-mortem analysis. Meaning, if that machine were to fail, whether you knew it was coming or you didn't, you want to be able to hold on to that oil in that machine. Let's say it's a gearbox. Hold on to that oil and see if you're able to extract information. Most likely you're going to have some level of wear debris or some level of changes in the oil that's in there from what you had previously in that machine. So all that information can tell you what happened, why that machine failed, what was that failure, can you avoid it in the future. This is very important. Obviously, the relative savings at this point for that particular machine is not going to be that high, but it's going to be able to help prevent that potential failure in the future. So this is also very important. If you've been performing oil analysis for a while, there's typically one thing you're going to look at first when you're reviewing the reports. You're simply going to look to see if the results are good or bad, right? And hopefully that's not the only thing you look at, but most reports will be laid out in a way that has an indicator towards the top suggesting this very detail. Usually there's some kind of shape or number or color or some combination of the sort. Green potentially meaning everything is good. Yellow, maybe we need to look at things a little more closer. And bad, that's going to be red. Something's wrong. Something that needs to be changed, and maybe the oil needs to be changed. Maybe the machine is showing some kind of wear debris. But what else are we looking for? In total, oil analysis has three main categories. Really, three ways of looking at the data that will influence each other. That is the health of the lubricant, such as viscosity, additive levels, this is fluid properties. The contaminants present in the oil, not just dirt, but we're also looking at things like water, anything really that's not supposed to be in that oil. And the third one is wear debris. This is this being an indicator of that mechanical wear has occurred on the machine surfaces. If a machine is going to fail, the lubricant will most likely find out first. This is exceptionally critical to understand. Many technologies intend to predict when a machine is going to fail by looking at the very specific events occurring. That means the machine is already in early signs of failure. Oil analysis can do this as well, but is also able to observe things a whole lot more than that, not just the wear debris indicating that wear has already occurred, but it's looking for events that may say that a failure will potentially happen in the near future. So looking at the lubricant or other foreign substances that can become present in the oil, which indicate not only the machine is already in an early sign of failure, but instead indicates the machine is currently in a state that will lead to a failure. Again, this is extremely important because if the root cause of a potential failure is observed before the machine itself is influenced by it, then it can be corrected proactively, leaving the machine without, potentially, any permanent degradative consequences. So looking at these three categories, fluid properties, you want to be looking at things that describe the oil, the base oil, and the additives and see how they've changed. So maybe you're looking at viscosity, maybe you're looking at the acid number, the base number, maybe some elemental analysis. With contamination, you want to look at anything that gives you indicators to something that's not supposed to be there. So particle count, that's important. Moisture level, that's very important. Patch test, flash point, anything that could become influenced or show a contributor to contamination in an abnormal way present in the oil. And third is the wear debris. So you're looking at things like ferrous density, because a lot of wear debris is going to be ferrous in nature. So the ferrous density will increase the ferrous concentration if wear debris is present. Analytical ferrography, that's a way for us to look at these particles in more detail and see where they might have came from, how they were produced. And elemental analysis, of course, is one of these that can probably go between all three of these categories because it's looking at elements of either the fluid properties, of contamination, and wear debris. So if we're looking at things changing in the fluid properties or the contamination, that's probably going to be proactive because that doesn't mean the machine has failed yet. But if you're looking at wear debris, again, that's going to be predictive. So So let's think about some of the costs and benefits and what you might expect from critical machines with oil analysis. Now, comparing what the cost may be for a well-implemented oil analysis program versus what the benefits may be, it may be the difference between 2% of your overall equipment value, that's the cost of the oil analysis program, versus the 20% of the actual annual benefits. So some costs here may be, the hardware, the labor involved to take the samples, the program management, the cost of the laboratory and the software and data management that may be part of the laboratory, may not. All that proactive maintenance cost. And some of the actual benefits that may be 5 to 20% of that equipment value is, sometimes they're hard to, quantify, but it's going to be that early root cause detection, knowing when a failure potentially could occur because of what's present in the oil. Early failure detection, so lower material and labor costs. So because we're avoiding a failure, we're potentially going to extend the life of your machine several times. And you're going to reduce the potential labor, potential material required, and the spare parts. Less production losses, lower energy environmental costs, increase in safety. Everything's going to become better as a result of a well-implemented oil analysis program that could be anywhere from 5 to 20% of a benefit as a result. So before I get too more in detail about the interpretation of oil analysis reports, I kind of want to review the entire checklist of an oil analysis program. These are the items that you really need to make sure you have implemented in your program in order for there to be a real level of success as a result. Any one of these things by themselves could potentially cause the entire program to not be that effective. The first group here is obtaining a representative oil sample. Everything you can do to make sure the oil you put into that bottle and send to the laboratory is representing what's happening inside your machine. You don't want to be able to introduce false positives or false negatives. So you want to select the right machines. You don't want to do every machine. You don't want to do only one machine. You want to make sure you're selecting the right machine. Using clean and correct sampling containers and extraction tools. Correct sample location ports and sample frequency, both very important. Probably could be separate checklist items here. Proper sampling procedures, making sure it's a consistent and correct procedure. And then forwarding that sample immediately to the laboratory. So you don't want that sample to be sitting on your desk for several weeks when the information in that bottle could indicate a failure, and by the time you get that result, it could be too late. The next group here involves the testing, so everything involved that's actually happening at the laboratory, the training and certification of the technicians and the optimization of the test selection, which you may be involved in that in addition to the laboratory. Correct sample preparation at the laboratory using calibration standards, low interference instruments. And on-site oil analysis and inspections. These are things that you may be doing in your own plant with some type of oil analysis, maybe using a vis gauge for some viscosity testing or something else that's more simple. But even the inspections you're doing on your machines, the visual inspections can provide you very important information to combine with what you're doing in oil analysis to give you a better understanding, a better interpretation as a result. The third category is determining the optimum course of action. Very important. So effective organization of the analysis with proper trending. So you want to see trend data. Accurate data interpretation by the laboratory, and then enhancing that data interpretation by the end user. The laboratory will hopefully be more understood and more educated in the test principles and how those work, and give you some basic information about that. And then you are going to be more involved in understanding what's happening to your machine most recently and what you know that might be unique about it. Something that could combine your plant knowledge with that laboratory interpretation to give you a better understanding of what's happening with that machine. And then, of course, you must take corrective action and determine the root cause. All this is about making sure we understand what we are going to do next now that we know what the result is. And also continuous improvement and sampling adjustments, always refining how often we need to take a sample, what we're going to do. and then utilizing oil analysis results as a key performance indicator to tell you the overall success of the reliability of your machines through oil analysis. So you want to avoid false positives and false negatives. These are things that can be very detrimental to an oil analysis program in giving you the ability to really have any useful interpretation of the results. So a false positive is something that the test shows positive, but the actual conditions are negative. So an example of that would be, let's say we used pre-contaminated sample bottles. This is example B here, where the bottle you used wasn't well kept, and it doesn't take that much contaminants that may be present in that bottle to actually significantly influence the results in the oil analysis reports. So you need to make sure you use clean bottles or ultra clean. There's ratings of bottles and how clean they are, and that's going to be dependent on what the sensitivity is of your machine and the analysis you're trying to get. So knowing the potential cleanliness of not just the bottle, but the overall equipment you're using to take that sample is going to potentially affect the results. So you want to be aware of that and not have a false positive. Now, a false negative is going to be something where the test shows negative, but the actual conditions are positive. That could be if you took a sample near the top of a reservoir, let's say, where things are a little more stagnant. And if there were contaminants, solid contaminants, they might have already settled down. So if you took a sample there with maybe, let's say, a drop tube method, the results would show that the contamination levels are low and you don't see any wear debris. But the real results may not be that case, because what's coming back from that machine return line would be where all that data is. And then once it gets to that reservoir, it then goes to the bottom, and that's not where you took the sample. So you want to be able to make sure your results at least give you either true positives or true negatives. A true positive is test that show positive, the actual conditions are positive. That could be a bad thing, depending on what you consider positive. And true negative means that the tests show negative and the actual conditions are negative, which is really what you want. Either way, you want to make sure the results you're getting, the tests you're running, are from a sample that is really the true information about your machine. The documentation of the lubricant and the machine are all very important information that needs to be in combination with the oil analysis reports in order for you to get a good interpretation. So just like a doctor, when you go into the doctor and they ask all kinds of questions, what have you been eating lately? What have you been doing to exercise lately? Anything different happened to you lately? All this information helps the doctor come to a conclusion about what might be good and bad about your health. So a doctor needs a complete personal health history, and so does your oil analysis. So when you register your equipment for lubricant analysis, make sure you give all that information. Make sure they're able to track the machine, so give the machine identification number or name, the unit type, give information about that machine, the manufacturer and model information, the lubricant manufacturer, what type of lubricant is it? Is it gear oil? Is it a hydraulic oil? What type of viscosity is it? What are the operating conditions? Is this something that's seeing a lot of starts and stops and shock loads? Is there high temperatures typically, or is it in a cold environment? What is it typically seeing? What is the overall work environment? What things could it be exposed to? Maybe there are certain types of elements in the air, airborne contaminants, iron ore, or something where you're located might be a higher chance of some type of contaminant. And lubricant application knowledge. This would include the total oil volume, how much oil is in that system. That plays a role in how quickly something could potentially show or be diluted by something being introduced. And accompanying lubricant sample, you want to make sure all the information is there so that they can give you good interpretation of the results before it's returned back to you, when you then give the higher interpretation based on what you know about that machine. Let's talk about what might be inside an oil analysis report. So here's an example of one, and there's all different types depending on which laboratory you work with, but they all have similar characteristics. This one here shows that the machine ID is shown towards the top, so the lubricant and filter information. All that information is usually what's provided by the plant to the laboratory, so they can help understand what the lubricant is they're working with and what some background information there might be about that machine. And then there may be an area that shows the overall condition. This, it gives you the quick information about what the laboratory saw in your results and if you need to take action immediately. In this case, the 4 that's red means that there's something that needs to be looked at immediately, and it's a severe condition. There's usually a section there that has some comments that the laboratory has written up based on their results. And after that, you have a lot of the raw data, including elemental data, all the elements, whether it's contamination related, fluid properties related, wear debris related. And then you'll see other areas of data where it could be the isocontamination code, the acid number, the moisture content, all kinds of information that of what you might have had in a test flight for this oil analysis report. You also want to be looking for where the baseline sample is. You always want some kind of reference point. So it's one of the most important parts of an oil analysis program is to always have baseline samples identified on each report. You want to look for hours of oil in service, hours of the filter, any top-up information. It's good to show trend graphs. Sometimes that's on the second or third page. Look for any data patterns. Also be aware of any test standards and calibration references, anything that tells you, what are they using to do the test itself, because it might be different compared to what a different laboratory might be doing. And also look for specific elements tied to additives and contaminants and wear debris, and also look for any other confirmatory indicators around that. So here's a brief look at all the different types of tests that could be ran and be shown on your oil analysis report. A big one, of course, is going to be viscosity. Viscosity, one thing it could potentially indicate is oxidation occurring, contamination, let's say. Be very concerned about significant decreases. A significant decrease in contamination should be alarming. It probably means there's something introduced that's contaminating and drastically. Maybe let's say a top-up was made with the wrong viscosity, a lower viscosity oil. Viscosity is one of these things that you may have an upper and a lower limit, and you know how much hot increase or decrease by percentage you're going to accept based on the various indicators of your machine in the oil. Acid number is going to indicate oxidation potentially. Base number, if you're going to be doing any kind of testing on an engine, let's say, base number is going to be important to test to determine what the detergent depletion levels are. As detergent gets used up, your base number is going to start to change, and that'll help you determine whether or not you need to change your oil. FTIR, they can indicate several things such as oxidation, nitration, and all these other things, and it's all very important to determine whether or not something is changing in your oil analysis. It could relate to something that is specific to a contaminant, or it could be a fluid property. There are many things that FTIR can indicate. Another one is RPVOT. That's a robust test that's not usually ran on every single routine test. It's a little bit more pricey. It's something that helps us estimate the remaining useful life. RPVOT stands for Rotating Pressure Vessel Oxidation Test. So oxidation is what we're looking at here. As your oils get used up in service, your additive levels are going to change. Antioxidants are going to go down, and that's going to cause the RPVOT values to go down as well. Another test that's similar to that is the linear sweep voltammetry test. That's also looking for the depletion of antioxidant additives. So basically the remaining useful life of your fluid, your oil, overall oxidation levels. This is all very important. And most of these tests we're looking at and talking about so far are going to require some kind of reference, some kind of baseline. So it's important to know what that baseline reference is, such as your new oil or a previous sample, so you know exactly what you should be expecting. Some other ones are particle counts, what the contamination and where metal levels are. Elemental analysis, this is something that can give you a great level of detail about potential wear debris, for example. Wear debris, though, with elemental analysis does have limitations on the micron particle size that's looking at. It's mostly looking at the smaller particles. So anything larger is kind of a hard time picking up through elemental analysis. That's why we want to pair it up with something like a particle quantifier or ferrous density, let's say. Ferrous density lets us look at including the larger iron wear debris. So as wear starts to get a little bit more vigorous, a little more intense, unfortunately, in the machine's condition, you're going to start seeing not the smaller particles, but larger wear debris particles as well. So having that ferrous density analysis and your wear part concentration will be able to let you know what stage of wear is occurring in your machine. Other elemental analysis would be additive elements or dirt levels or glycol contamination. All these things will be indicated in elemental analysis. Much like other aspects to the oil analysis reports, additive elements, the best way to monitor these is with having a frame of reference, and that's going to be your baseline oil sample. So you need to know what your new hydraulic oil, your new engine oil, your new gear oil is expected to have in parts per million of zinc or phosphorus or calcium, magnesium. That way you can look at your in-service oil and figure out how much is depleted and figure out where you're at. So I'm not going to spend too much time on this table here, but this gives you an idea of the common test slates by machine application. You'll see all the standard tests on the left side there and some different machine applications towards the top. The R's indicate things that might be done routinely, and the E's represent something that might be done by exception. So every type of machine application may have a different type of routine test slate ran, although you'll see there's some things that are done very commonly as a routine test slate, such as particle counting or viscosity testing or water content testing. Those things you should probably have as a standard on every single one of your oil analysis test slates, and you should expect to see that on every single oil analysis report. So keep an eye out for that. As we look at the first category of oil analysis, the fluid properties, we're trying to figure out what's happening to the base oil and the additives over time. So we're trending data here. We want to trend viscosity, additives, the acid number, any indicators of oxidation, all of which they're starting to move up or down. But at some point, they may start changing more drastically, and that tends to happen near the same time. At that point, that's when we want to start planning for a condition-based oil change. You'll see here the viscosity and the acid number. There's an inflection point when they both started happening. They're starting to have a change at the exact same time, and maybe that means oxidation has started to occur more rapidly, probably because the antioxidants have become now depleted. These are probably the four most common root causes that have the greatest negative effect on the lubricant's aging process. They can affect the oxidation individually or just overall degradation, or when they're in tandem, in combination, they really have a destructive power towards the aging of the lubricant. So heat is a big one. We've heard of the Arrhenius rate rule. For every time you increase the temperature by 10 degrees Celsius or 18 degrees Fahrenheit, half the life of the oil. Water in oil can increase the oil degradation rate by more than 10 times. It doesn't take much water in the oil to really start having a negative effect. Air as well, not really talking about the air that's sitting in the headspace, but the aeration of the oil, the air that's inside of the oil, especially when water is present as well. And also metal can act as a catalytic substance leading towards a degradative property, such as oxidation in the oil itself. Viscosity has the potential to trend upwards or downwards. In either direction, you need to have a cautionary limit, which is the point at which you need to start paying it more attention. You have multiple data points that hit the cautionary limit. That means you need to take action. And then you have a critical limit, which if there's even just one data point hitting the critical limit, you need to start taking action. All this comes back to what your new oil baseline is. So even though it might be an isoviscosity grade of 100, it doesn't mean the Cinestokes is 100. It could be 92, 95, 97, 105. Whatever it may be, that's your point in which you need to go up or below the percentage of what your viscosity limits are going to be. Like I said, viscosity is one of these things that potentially could go down or could go up. So you need to have a lower and an upper limit. And what will affect the viscosity go up or down could be a change in the base oil itself, so molecular change. Something is changing chemically to the base oil to cause it to increase or decrease the viscosity. Or something could be happening where there's an addition to the oil, contamination, for example. So some things may be correctable, as you're seeing with the green squares here, and some things are more permanent, non-correctable change. That's the circles here. Most of the things that happen to change the base oil's chemistry will be more of a permanent change. So an increase in viscosity, that would be like oxidation, polymerization. A decrease, you may have thermal cracking in the oil molecules. Something is causing the molecules to break apart where the average molecular size is then smaller. So that's like shear thinning or hydrolysis. Things that could be added to the oil to cause a decrease would be something like fuel, refrigerants, and solvents. These things are thinner than the oil itself typically and will cause the viscosity to go down. And even the wrong oil. Wrong oil could be the viscosity of the incorrect oil that was topped up in there. Could be a lower viscosity or a higher viscosity. So that's one that you don't know which one it is. It could decrease the viscosity or it could increase. And certain things could be introduced to the oil to cause an increase in viscosity. Water, for example, which by itself, the apparent viscosity is actually lower than oil. When it's turned to an emulsion into the oil, the viscosity actually shows an increase, and even in trained air. And also things like soot and antifreeze, if they're contaminated into the oil, you're going to have an increase in viscosity. So when you're interpreting an oil analysis report and you're seeing these trends over time of viscosity going up or down, whatever it is, you need to be able to understand what could potentially cause that change. And then once you're trying to investigate that, you're going to be looking at other indicators, other parameters on your report or information, historical data about your machine to say whether or not which one of these may be more likely. Is there potential for one of these contaminants to be introduced? Is there potential for oxidation to occurring because of what you see in the ruler test or the RPVOT test or acid number test? All these things need to be looked at in tandem to figure out whether or not you can have a better ability to conclude onto what's happening to your oil. So here's a case study showing the viscosity trends of an isoviscosity grade of 68 hydraulic oil. Now, the baseline here is showing 65 smooth stokes. This is a reminder that you want to be able to use a baseline test to know what the viscosity was when you first introduced the oil, not necessarily what the isoviscosity grades, because those could be a little bit different. Here you're showing the trends occurring. First, there was some viscosity shear thinning, so the viscosity went down a little bit. There's a top-up with rebaselining at that point, so a top-up with the oil that was similar or the same as the baseline of 65, so that's why it went back up. But then it continued to go back down a little bit. Right now, we're still within that upper and lower range there of about 10% up and down, so that's okay. But then a wrong oil was added with the wrong viscosity in the top up. You see it go quite a bit above that range, so that's when we're starting to realize that we need to start taking action and figure out what's going on. And then later on, an FTIR confirmed that an incipient oxidation was actually occurring. So as a result, a baseline was done and with an oil change, and the oil analysis is now back to within that range, and now you have a new baseline with this new viscosity grade. When you're doing viscosity analysis on your oil analysis reports, here's a flow chart you can use to kind of break down what you're going to be doing. First, you're going to have a baseline new oil result showing, and then you have your upper and lower limits. Then you're going to be doing some routine analysis. It could be every 2 weeks, every month, every 2 months, whatever it may be. Eventually, you're going to get a result of viscosity that's not conforming, whether it's under limit or over limit. Either way, you need to then figure out what that corrective cause is and then change the oil as required and go back to routine analysis. Whatever it is, you need to make sure you figure out what that root cause was so you try to avoid it from occurring again. Now let's talk about the second category of oil analysis. That's going to be contamination, looking at how to control that contamination. The contamination is not just those solid particles like ambient dust in the air and so forth, but also the moisture that might be present in the oil or any excess air aerated into the oil, the wrong lubricant, soot, radiation, even heat, something like anything that's not supposed to be there is considered a contaminant. So when we're trying to control contamination, this is because this is the primary cause of wear and lubricant failure. This is how you're going to build a proactive maintenance program. Now, contamination is very important. Contaminants, like I mentioned, could be all sorts of things, and they can affect the actual oil itself or directly impact the machine. How it affects the oil could be a chemical reaction such as oxidation, which we mentioned before. The solid contaminants can do that. Water can do that. Glycol can do that. Air can do that. Heat can do that. Many things can cause oxidation to become promoted. It can also change the physical properties of the oil, particularly things related to viscosity, whether it's a viscosity change or viscosity index influence or flash point, let's say. All these things can be influenced by the contaminants. Now, of course, contaminants can affect the machine surface themselves. Looking at the machine surfaces, it could become that surface wear, the wear mode, whether it's fatigue wear, whether it's abrasive wear. It could have cavitation wear. It also could chemically attack the surfaces with, let's say, corrosion through the acidity in the contaminant. It can lead to deposits as a result of the actual contaminant and lead to more a chemical reaction on the surface. So the most common way that solid contaminants are tracked and reported on an oil analysis report is through this ISO 4406 solid contamination code. Here you have an example shown in the middle here of 18, 16, 13. That's an example of what may be seen on a report. Those three numbers are referring to particles greater than 4 microns per milliliter, 6 microns per milliliter, and 14 microns per milliliter, respectively. So that 18, for example, as you see here on the Renard series table on the right, is referring to a number of particles that is in the range of 1,300 and 2,500. In this case, it's 1,752 particles greater than 4 microns per milliliter. Similar thing here, the 6 microns per milliliter, there's 517 particles. That's a range number of 16. And the third one is 55 particles greater than 14 microns per milliliter. That's a range number of 13. So that summarizes all that data into three numbers, 18, 16, 13, to give a description of what the contamination levels are like in that sample. Now, one important thing to notice here is that every single number increase is, on average, double the number of contaminants. So if you go 2 numbers up, you're going to see 4 times as many particles. So if you went from 18, 16, 13 to 20, 18, 15, you're going to expect to see the double the number of particles in that sample. So tracking the levels of contamination in your sample is very important so you can trend that data over time and see when you start seeing an inflection, something that's starting to spike up and go to a direction that is unusual. It's not what you typically see in that machine. Once you know that you have solid contamination increasing or a level that you're not okay with, you need to figure out where that particle contamination is coming from. So solid particle ingression can come from all kinds of sources, as you can see here. It can be built in, such as service debris, manufacturing debris. It can become ingressed, or it can be also generated. Generated would be on the surface, let's say mechanical wear, corrosive wear, cavitation, or the oil itself can cause, or can be the introduction of a contaminant. But when we're talking about solid contamination, often we're really talking about what is getting ingressed. When I say ingressed, that's something coming from the environment or the process or some kind of combustion blow-by zone. Whatever it is, that's when we're going to lead towards a more detailed oil analysis approach to figure out through elemental analysis or other forms of analysis to figure out exactly where that particle might have came from. Now, I'm not going to go into too much detail here, but this gives an example of particle types and what their sources could be, whether it's built-in, ingressed, or generated from within, and what their appearance may be. You see some pictures there below. These pictures are important because you should be able to use different types of oil analysis tests, analytical porography, for example, to figure out where this wear debris or other solid contaminants is actually looking like, and that helps us figure out where it came from, how it was produced, what the wear mode was, what its source is. As you look at the third category of oil analysis, wear debris, we need to know what causes changes in wear debris concentration. So an increase would obviously mean something is happening in the machine. It could be an increased loading. It could be a misalignment. There could be corrosion occurring. That's when you need to take action to do exception testing to figure out what that might be going on inside your machine. A decrease in wear debris, well, that could be maybe filtration. The filter is actually pulling out all those contaminants. Maybe they're settling. So if you took a sample from higher in a reservoir, all that wear debris might be settling to the bottom compared to where a different sample might have been taken. So you need to be aware of what could potentially cause an increase in wear debris or a decrease, and then perform other tests to be able to confirm those results. So there are several technologies you're going to use to help you analyze the wear debris. And some of those that come along with some of the standard routine analysis that's shown on a typical oil analysis report. Some that require a little more in-depth testing being done. Those are called exception tests, and you don't do those routinely. Either way, the best way to really figure out what your wear debris is to break it down to 5 main categories. What the elements are, how big they are, what their shapes and textures may be, what the metallurgy is, so where in the machine it might be coming from, and what the overall concentration is. And that's going to be able to be observed through different types of technologies such as spectrometric analysis, that's your XRF, that's your rotating ditch electrode, that's going to be your ICP. All those results are going to be presented in parts per million. There's going to be some limitations there, which we'll talk about in a second. Ferrous density analysis, your ferrous particle counting will tell you the overall concentration of those ferrous particles. Typically, that's what wear debris will be if it's a ferrous metal. And this analysis will be able to not just show the smaller particles, but also the larger particles. And then the overall wear particle identification. In this case, we're probably going to need to put something under a microscope, whether it's we call it a ferrogram or a filtergram, something where we can analyze it under a microscope to figure out what the overall shapes and sizes are and what the overall concentration may be to give you a better identification of how it's produced. The shapes and sizes and textures are the clues to figuring out what the wear mode was, whether it was adhesive wear, abrasive wear, fatigue wear, corrosive wear. All these different wear modes are give you a clue as to what's happening in your machine. Remember, oil analysis is all about trying to figure out what is happening inside your machine that you can't see from the outside. And using this wear particle identification is your opportunity to figure out, is this happening in this part of the machine or that part of the machine? Is it happening because of high temperatures? Is it because of a lack of additive? Is it because of a lack of viscosity? All these things can be determined based on what you're seeing in your wear debris analysis, just like you're seeing here. With elemental analysis, that's going to be a big portion of your report. It's going to give you data about all the elements and what the overall parts per million, the concentration, say, of that element is. And that element could be related more to the contamination or the wear debris or the additive elements. Certain ones are going to trend up, certain ones are going to trend down. Ones are going to trend up are more like wear debris and contamination because you expect those to go from a place where you hope they stay at a lower level and may increase to a point that you need to start being concerned. And oppositely, additive elements may start to go down, and that's when you start being concerned whether or not they're not able to protect your machine as much. So as you can see here, of all the different elements, there are many sources these elements could come from. And they could be built-in wear, they could be generated from within during in-service use, or they could be contaminants from the environment or the product all kinds of sources. Whatever it may be, you need to better understand your environment, your machines, operating conditions, what the potential sources could be, and use lists like this, use different source books. As you can see here, the source sample of a resource you could have to know your elements. It's important when you're doing wear debris analysis. And like I mentioned about looking at the shapes and sizes and textures of the particles, that can be analyzed under a microscope through analytical porography and other techniques, and I'll be able to tell you where that piece of wear came from, whether it's cutting wear, adhesive wear, abrasive wear, corrosive wear. The red iron oxides can mean rust, for example. All these are different clues to be able to figure out what is happening inside your machine. So to summarize the approach you're going to use for wear particle analysis, there's all kinds of techniques, whether it's a spectrometric analysis, even particle counting. Particle counting we're looking at for just overall contamination, but the particle counts will go up if wear debris is also going up. Usually the wear debris is going up also because of the solid contaminants that are increasing in the oil. Direct image particle counting, ferrous density analysis, analytical porography, all these are various techniques you want to be able to use in tandem, undersize what their size range restrictions are. Some are better at looking at smaller particles like spectrometric analysis. Some are better at looking at all the larger particles, particle counting, for example, ferrous density, and understanding what that could detect, how often you should be performing that analysis. So some are routine and some are only by exception. Of course, wear debris is a very important aspect to oil analysis. It's the part that tells you, hey, there's a failure already starting to occur, and you need to figure out a solution quick enough. But wear debris can be kind of complex, and you have to learn various techniques to be able to maximize what you can gain from it. There's all types of techniques, such as normalizing elemental data to rate of wear based on the number of hours of operation. This is something that's a little more advanced, and it will take time to make sure you can properly create your trend graphs to reflect that. Also, changing or normalizing your data based on the top-ups added to the machine. Sometimes your oil analysis laboratory will be able to make these changes to your trends if you provide the right data. So it's very important to let the laboratory know what's happening. Of course, you want to recognize elemental families. Certain elements tend to trend together, even if it's wear debris or solid contamination or fluid properties like the additives. Certain elements will trend together up or down, and knowing what those families are is an important skill to be able to interpret the results of elemental analysis. You want to use statistical limits based on standard deviation, understanding particle size sensitivity based on the wear debris technology. I kind of just went over that a little bit. And you want to utilize analytical porography to analyze the shapes and textures and other visual characterizations to help identify the various wear modes, how that particle is produced, and what you can do to figure out the best solution, the best corrective action. Interpreting the results of your entire oil analysis reports, you want to make sure you have a systematic approach to reviewing all the data. This list here will help kind of summarize some of the things we discussed already, but it's also a good checklist of things you should consider as you go into each one of these reports. You'll get better and better at it. Now, first, of course, you want to make sure you see the oil name, the viscosity, all that equipment information, oil information that's relevant is there to help you create a better conclusion of what other results are showing. Overview of timing, check the date to find out the oldest sample, the newest sample, and see what the trends are. You want to look at know what the sample location is. If you had a good sample location or a bad sample location, whether it was from a return line or a reservoir, or maybe it was done in a procedure with a certain maintenance tech that maybe is less familiar with the procedure, and that could help understand why that result was different. Have a new oil baseline. Of course, I've mentioned that several times. It's very important to be able to know what the new oil should look like so you can know whether or not this used oil, this in-service oil sample is quite different or not. Does the additive element's fingerprint and viscosity match up to the oil listed above? That's looking back again at the baseline. How is the condition of the oil, the health, the overall health, the remaining useful life, looking at the oxidation levels, whether or not you've been able to test with the linear sweep voltammetry or RPVOT or acid number, viscosity. All these things can help determine what the overall condition of the oil is. How is the condition of the equipment? Of course, that's wear debris, for example. And you want to normalize that to your run hours. Are there any significant contaminants present? Obviously, the big ones are going to be solid contaminants, dust in the environment. That's going to be silica primarily and alumina. But maybe there's something else there that's a bit unique, something that may tie with your environment, and it says this machine has typically seen this type of contaminant, and we need to be aware of that. Of course, you want to always look at the trends for all data, viscosity trends, acid number trends, all the elementals, particularly the big ones with the families that mean something together. Trend that data to see if that is going in the same direction and what that might mean. Have any abnormal or critical data points been reached? Develop conclusions, recommendations, look at what the laboratory is telling you, but don't let that be the only conclusion. You have to put that together with what the lube techs are telling you, what is the historical information about that machine. Compare all those comments and recommendations and understand what may be the best result, the best course of action, and figure out how we can avoid the root cause from happening again. So let's say there was a negative result. We did see higher moisture or higher solid contaminants. Not only do we need to have a corrective action here, but we need to make sure we understand that root cause could come back, and what can we do to avoid it. So maybe it means having better breathers on your machine or having better filtration procedures to make sure your machine can get that contaminant out of there once it's introduced. Or making sure you can avoid the moisture from getting in from other sources. Whatever it may be, you need to have a better understanding of how to avoid that problem from happening again in the future. So oil analysis is a tool, right? And a tool for your lubrication program. You need to make sure that you are operating that tool properly. Like I showed you in that checklist, there's several things that you need to make sure you're doing correctly in order for you to expect success from your oil analysis program. I suggest that you review that checklist and see where your oil analysis program may be deficient or you may be needing to improve upon a little bit. But to kind of summarize some of the things we talked about today and how to maximize the life of your oil analysis program, the value of your oil analysis program, you need to make sure you know what questions you're trying to answer and know what tests can tell you what that answer is and to pair that up properly. You don't want to neglect other checklist items in your oil analysis list there. Always ensure your machines and lubricant data are on the report. That way, the oil analysis laboratory technicians can properly figure out whether or not that result that's showing could make sense or not. Always ensure relevant historical data in the report, such as top-ups of failures, recent failures potentially, are in the oil analysis report so they can use that data. Always keep a new oil baseline for reference. I've said that several times. Sample routinely and have an optimized frequency. I didn't talk about that very much, but it's an important aspect to know, okay, well, we're going to be sampling on this machine, but we need to sample just enough to where we can be able to detect a failure before, or not failure, but detect a potential failure, an incipient failure, or maybe even better, a root cause that could eventually lead to a failure before it starts to get worse. And you don't want to sample too infrequently to where that period between you start seeing that root cause or start seeing that incipient failure and the time between the actual failure, it's all within the entire range or entire frequency, and you never got to see the actual result. And then know the three categories of oil analysis: fluid properties, contamination, and wear debris, and how they influence each other and what their overall significance is. You want to see how that plays a role in all the various areas of the oil analysis report. So as I mentioned, my objective today with this webinar was to give you the opportunity to learn about how to maximize the value of your oil analysis reports with quality interpretation techniques. With that being the case, I really do hope you've learned something today and we'll be able to apply some of that, what you've learned at your facility. If you have any questions at all, feel free to submit them in the Q&A window or contact Noria using the information on the screen. We want to help. Whether it's answering your questions or visiting your site to begin an assessment, we want you to be successful. So again, thank you for joining me today, and please remember to send your requests for the next webinar topics below.
Thank you, Bennett, for that excellent presentation. If you enjoyed today's webinar, visit Noria.com for information on Noria's online certification courses, or register for our next public training course in your area. You can also bring Noria on-site for personalized private training. To suggest a future webinar topic, simply type it into the Q&A window now. Again, thank you for attending this webinar, and we look forward to you joining us for our next webcast presentation.